everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to know that a radical is a species with an unpaired electron and is represented in mechanisms by a single dot, and how it's formed by homolytic fission of a covalent bond and results in the formation of radicals. And then we're going to understand the reactions of alkanes with oxygen and air and halogens in terms of the mechanism of radical substitution through initiation, propagation, and termination steps. And then we're going to understand the limitations of the use of radical substitution reactions in the synthesis of organic molecules in terms of further substitution reactions and the formation of a mixture of products. And then our last learning objective is to understand that heterolytic bond fission of a covalent bond results in the formation of ions. We're first going to look at covalent bond fission. And what we mean by fission is just breaking. So covalent bond fission is just the breaking of covalent bonds. And so we can break up a covalent bond in two different ways. The first way is heterolytic fission, and this means that when the chlorine-chlorine bond breaks, we're just using chlorine as an example, but when this covalent bond between the two chlorine atoms breaks, both electrons end up on one chlorine atom, and so ions are produced. So the chlorine on the left has managed to get both of the electrons because they used to share the electrons in the covalent bond, and one electron came from each one of the chlorine atoms, but the one on the left has now ended up with both of the electrons, so it's turned itself into a negative ion, whereas the one on the right has lost both of the electrons, so it's lost one electron that it had originally, and so it becomes a positive +1 ion. The second type of covalent bond fission is homolytic fission, and this is when each of the electrons in a single bond goes to each chlorine atom. So we have the normal chlorine-chlorine bond, the covalent bond, which is a shared pair of electrons, and it breaks apart so that they both go their separate ways with however many electrons they had in the first place. And this creates free radicals, which are very, very reactive, and we notate it by using a dot. So we write it Cl dot. Now we're going to talk about the chlorination of alkanes. So in the presence of UV light, alkanes react with chlorine to form a mixture of products with the halogens substituting hydrogen atoms, and so we form a halogenoalkane or a haloalkane. So the definition of a haloalkane is a group of chemical compounds derived from alkanes containing one or more halogens. So in this example, we'll be looking at CH3Cl, which is chloromethane. And the really important thing to remember about this is that it is a free radical substitution reaction. And so our example is methane reacting with chlorine. So this forms chloromethane and also hydrochloric acid. So we need to remember our 3 steps of free radical substitution reactions. So in the first step, the chlorine bond breaks, and we have to remember that it's in the presence of sunlight. That's really important. And this forms our chlorine free radicals. And also remember that for initiation, breaking the Cl-Cl bond, we can break it homolytically or heterolytically, where heterolytically means that one of the chlorines gets both of the electrons of the bond, so that ions are formed, whereas homolytically means that they both get their electrons back, and so 2 free radicals are formed. So in this case, in initiation from free radical substitution, homolytic fission happens of the covalent bond. And now on to the second step, we have propagation. And propagation has 2 steps. So the first step is that the chlorine free radical reacts with methane, and this forms hydrochloric acid and also a CH3 free radical. And this CH3 free radical then reacts with more chlorine to form chloromethane and also a chlorine free radical. And so because we form a chlorine free radical, this is the chain part of this chain reaction. And the last step is when free radicals react with each other and are removed from the reaction mixture. So now we're going to have a look at this reaction. So the first step is initiation. So number 1 is initiation, and what happens is that this chlorine bond, this covalent bond, breaks homolytically. So we've got Cl, Cl, and that's the covalent bond that I've drawn. And this, under the presence of sunlight, so we write UV, forms two of these free radicals, which we denote by Cl dot. And these are really, really reactive. And so these are what are used in propagation to form the chloromethane. And so the second step is propagation. And what happens first in the first step is that a chlorine-free radical will react with the methane that we have, and this will form, it'll take away, the free radical will take away one of the hydrogens from the methane, so we'll form hydrochloric acid. And then that means that the methane will be left with one less hydrogen, so that itself is a free radical. And we always put the dot where the atom is missing. So the hydrogen is missing from the carbon, so we put the dot on the carbon. And the second step is where we have this CH3 free radical reacting with chlorine, and this will form our chloromethane, so CH3Cl, because basically it takes one of the chlorine atoms from the chlorine. And so we get a chlorine free radical. And so this is the free radical that goes and then repeats these two steps. So this is the chain reaction. And then thirdly, we have the termination step. And what happens here is that two free radicals then react together and remove themselves from the reaction mixture. So we can do this in a couple of ways. So we can have two chlorine free radicals reacting to form chlorine, or we could have a CH3 free radical and a chlorine free radical reacting to form some more of this chloromethane, or we could also have two of these CH3 free radicals reacting to form CH3CH3. And so these are three steps for this reaction. So then overall, what we have is that we started off with some Cl2, so we've got some chlorine, and we reacted it with this methane here. And then what we produced was this hydrochloric acid, and we also produced this chloromethane. And that's because if you have a look at this free radical, we've formed it in the first equation, but we've used it up in the second equation. So this is what we would call an intermediate. So it's not included in into the actual reaction. Now we're going to talk about combustion of alkanes. So alkanes are used as fuels, and fuels are substances which produce energy when burned. And this is because they readily burn in oxygen in a very highly exothermic reaction. This also explains why we use them as fuels, because if it's really highly exothermic, that means we can generate a lot of energy coming out of it when we burn them. The combustion of alkanes and other organic compounds can be complete or incomplete. So when we talk about complete combustion, this is when there is enough oxygen. So there's an excess of oxygen, there's more than we actually need. And this type of combustion produces carbon dioxide and water. So for example, we could have hexane, which is C6H14, and this will be a gas. And if we add some oxygen to it, then we would form carbon dioxide and water. And now we need to balance it. So you've got 6 of these carbons, and you've got 14 hydrogens on the left. So that means we need 7 hydrogens on the right, and you've got 12 plus 7 is 19 oxygens on the right, and so we have 19 over 2 oxygens. And this would be an equation for complete combustion because we're producing carbon dioxide and water. The other type of combustion you can get is incomplete combustion, and this is when there's a lack of oxygen, so we don't have enough to completely combust it. And this type of combustion produces carbon monoxide and also solid carbon. Now, solid carbon we also call soot, and this can lead to global dimming. Which is where lots of these little particles will absorb sunlight and reflect it back towards the sun, so we get less sun on Earth. And also it produces carbon monoxide, which is a highly toxic gas. So an example of this could be if we had hexane again, and we formed, we added oxygen, and we formed carbon monoxide and water. And then to balance, we would have 6 carbons and 7 waters, and then we would have 13 over 2 oxygens. So if we have a lack of oxygen, then carbon monoxide will be formed instead of carbon dioxide. And this carbon monoxide is very, very toxic. And it's also known as the silent gas because it can replace the oxygen going around your blood, and your blood can carry around carbon monoxide instead. So then you'd have a lack of oxygen, and so you'd find it really hard to breathe. Now I'm going to talk about the limitations of these free radical substitutions. Now, the main limitation of using these free radical substitution reactions in the synthesis of organic molecules, meaning just making organic molecules, is that further substitution could occur where we have excess chlorine, and so this promotes further substitution to produce CH2Cl2, CHCl3, or even CCl4. And this means that we will end up producing a mixture of products instead of just the CH3Cl that we were after in the first place. So, for example, when we look at methane and chlorine reacting, we want to produce chloromethane. But if we have an excess of chlorine, we can end up producing all of these other three as well. So the first one is dichloromethane, because now we have substituted 2 chlorines. And then the next one which can be produced is a trichloromethane. And the last one which can be produced is a tetrachloromethane. And basically what happens is that more propagation steps will occur. So for example, if we look at the CH3Cl, so we have CH3Cl, and if this reacts with excess chlorine, that means from the excess chlorine, there will be more chlorine-free radicals. And so then this will react, and then the chlorine-free radical would take off a hydrogen from the CH3Cl, so we would get a free radical of CH2Cl and also hydrochloric acid, or hydrogen chloride gas, sorry. And then in the second step, we would have this free radical reacting with chlorine to form the CH2Cl2 and reform this chlorine-free radical. And then this CH2Cl2 can then go on to form CHCl3, and this CHCl3 can then form the tetrachloromethane, the CCl4. And so you can see that we can actually go through loads and loads of free radical substitutions, and so we'll get a mixture of products. Now we're going to look at some questions. So for question 1, write out the steps to this free radical substitution reaction. So the first thing we need to remember is that free radical substitution comes in 3 steps. So the first step is initiation, the second step is propagation, and the third step is termination. So the first step is initiation, and in this step we form the free radicals. So we use the chlorine, and under UV light, we can break the Cl-Cl bond homolytically to form 2 of these chlorine free radicals. So this is all that happens in the initiation step. And then in the propagation step, we actually do 2 things. So the first thing that happens is that a chlorine free radical will react with the molecule that we have. So in this case, we have fluoroethane. And what the chlorine free radical does is it takes away a hydrogen from one of the carbons. And in the equation, we see that at the end attaches to the carbon which is not attached to the fluorine. And so this means that we have to take a hydrogen off the carbon which is not attached to the fluorine here. And this forms the free radical FCH2CH2. And remember that for the free radical, the symbol that we use to denote is the dot, and it has to be on the carbon which has just lost the hydrogen. And so that's why I'm going to put it on top of the carbon this time. And we also form HCl because the chlorine free radical has taken the hydrogen from one of the carbons and reacted with it. And then in the second step, what happens is that the new free radical that we formed reacts with more chlorine, and so this forms the molecule that we're after, so the FCH2CH2Cl. And then what's formed is another chlorine free radical, and this chlorine free radical then goes and does these 2 steps again and again, and so this is the chain part of the chain reaction. And then the third step which happens is termination. So basically it's the end step. And what happens during termination is that free radicals react together and remove themselves from the reaction mixture. And so we can do this in 3 ways. First way is 2 of these chlorine free radicals reacting to form chlorine, or we could have a chlorine and a FCH2CH2 free radical, and this would form some more of this FCH2CH2Cl. Or the third thing we could do is have 2 of these FCH2CH2 free radicals reacting together. And these are our 3 steps for free radical substitutions.